Hi, friends. Welcome to the session. Good morning, good afternoon, or good evening, everyone, depending on where you are joining from. Welcome to today's session AI driven NTN satellite in 5G, 6G, a game changer. Before we begin, let's quickly review where we are. In our previous session, first three topics were discussed. These three topics were discussed. We covered the fundamentals of NTN and satellite communication. We discussed what non-terrestrial networks are and how they extend connectivity beyond traditional terrestrial networks using satellites, using HAPs, right? High altitude platform stations, etc. So just for your information, from now onwards, I will use TN for terrestrial networks and NTN for non-terrestrial networks. Okay. And we also explored the major NTN use cases and requirements like remote and rural connectivity, aviation, maritime, disaster recovery, etc. And in addition to that, we have recovered uh, and we have discussed like key performance requirements such as coverage, latency, reliability, etc. Right. In addition to that, we also covered 5G and TN architecture. So where we learned how satellites integrate with 5G networks and reviewed key components such as the satellite, G Node B, NTN gateway, and the 5G core. So today we'll continue with the remaining topics. So we'll start with NTN network operations. So here we will understand procedures such as network access, registration, session establishment. Also, we'll see the adaptation needed to handle satellite specific challenges like propagation delay, Doppler effect, etc. After that, we'll discuss deployment considerations like spectrum, link budget, mobility, all other different aspects which are unique to NTN. And finally, we'll explore AI as an intelligent 5G, 6G, and NTN integration. So we'll try to cover as much as possible. And if any topics remain, we'll continue then in the next session. So in our previous sessions, we have covered various topics like satellite communication overview. We also discussed various advantages and disadvantages of satellite communication. After that, we looked at what is one-way communication, what is two-way communication, and broadcast, multiclass, point-to-point, all these things we have discussed. Also, we then explored the satellite communication signal flow. In addition to that, we have covered parabolic antennas, which is like the heart of satellite communication. We have gone in detail of parabolic antennas. Next, we looked at the satellite frequencies and bands. What are the various kinds of bands that can be used in NTN, like C band, X band, KU band, and Ka band? We then explored various types of earth stations and communication platforms as well. After that, we examined what is non-terrestrial network, what are the different kinds of orbits, what are the different kinds of heights, what are the different kinds of footprint size, orbital period, all these things we have discussed in our previous session. And in addition to that, we had explored use cases and requirements. So here we have seen what are the applications of NTN, like smart cities, remote healthcare, aviation, military, defense. Following that, we also covered what are the key challenges to consider for a NTN, right? So NTN, there is lots of distance between transmitter and the receiver, right? Because satellite are in the space. So there are some unique challenges to consider for NTN. So we have gone through those challenges as well in the previous sessions. Following that, we covered what is transparent payload, what is regenerative payload, what is feeder link, what is service link, and we have gone through the architecture of NTN in details. Next, we looked at to what is fixed earth coverage beams, what is tracking area moverage coverage beams. All these things we have discussed in our previous session. And we have also compared what are the similarities between 5G NR interface and what are these and the normal 5G NR terrestrial networks and 5G NR air interface NTN, right? So we have compared both those networks. So these things we have covered in our previous sessions, right? So before jumping to the topic, let me briefly introduce myself. I'm Gaurav Goyal, and thank you so much for taking the time to join today's session. I truly appreciate your support. I will do my best to make this session useful, practical, and worth your time. So, let me briefly introduce myself. I have around 20 years of experience in the telecom industry, mainly in the wireless network. So, over the years, I have worked in RF design, network planning, optimization, and in building wireless solutions called DAS, right? So, I have expertise in DAS. So I have been fortunate to work with leading US telecom operators such as AT&T, Verizon, T-Mobile, Dish, as well as global companies like Nokia, Ericsson, Samsung, and Infovista. In Infovista, I contribute to the Planet RF planning tool for their product called Planet, right, which is the RF design tool. And before moving to United States, I worked on telecom projects for various countries like India, Nigeria, Japan, Finland, and UK. So these opportunities gave me valuable international experience and exposure to different network technologies and deployment strategies, right? And I began my career with 2G era and then worked through 3G, 4G, and now 5G. And today, my primary interest includes 6G, AI in telecom, public safety DAS, NTN, and the satellite communication. Friends, technology is evolving faster than ever. And that is one of the reasons I enjoy conducting these sessions. They give all of us opportunity to learn together and stay current with latest developments and prepare for the future of wireless communication. So this is a brief introduction about me. So I would like to connect with you. And so I have shared my LinkedIn connection on the comment box. So can you write yes? Are you able to open that link? Also, I'm not selling you anything in this webinar or in this training. So so only one request, please subscribe to my YouTube channel. So in future, so that you can have more videos like this. So can you confirm? Are you able to open those links, please? Thank you. Okay, thank you, thank you. So these are my few iCards. So these are not just iCards, they represent milestones in my telecom journey. So each badge reminds me of the project's challenges and lesson learned while helping build wireless networks from 2G to 5G, NTN, and now exploring 6G and AI driven networks. So they are more than company IDs, they are memories of a journey I'm proud of. So when I share telecom knowledge, it is not just theory, it's experience gained from real world deployments, right? And like in every webinar, let's quickly go through few quotes which I like and which I want to share with you. So remember, my friends, success is not built only on achievements, it is built on lessons we learn from failures. So you don't become successful by avoiding mistakes, you become successful by learning from them, improving yourself, and never giving up. So take the example of Rahul Dravid, one of the greatest and more respected cricketers, right? He once shared that in around 604 innings, he was out for less than 50 runs in 410 innings. So this means he didn't reach a half century in nearly 70% of the innings. So yet today he is remembered as one of the finest batsmen in cricket history. So what's the lesson? So failure is not the opposite of success. It is part of the journey to success. So every setback teaches us something valuable. So if we keep learning, keep improving, and keep moving forward, success will eventually follow. So that is a mindset I believe is equally important in telecom, technology, and in life. So keep trying, keep believing, and keep moving forward. Friends, this is one of my favorite success diagram because it's very simple but very powerful. So it shows that no matter what result you get, the answer is same, keep working. So if you don't get results, don't quit. It simply means you need more time, more efforts, or maybe different approach. So if you have bad results, don't get discouraged. Analyze what went wrong, learn from your mistakes, make improvements, and keep moving forward. And even if you get great results, don't become complacent. Celebrate your success, but continue learning and growing because there is always another level to achieve. So, whether your results are good, bad, or even if you see no results at all, the message remains same. Keep work. This applies not only to your careers but also to learning new technologies like 5G, AI, 6G, NTN, etc. At first, many concepts may seem difficult. You may not understand everything immediately, and this is perfectly normal. If you don't understand anything first time, that is perfectly normal. The key is keep learning, keep practicing, and keep improving. Remember, my friends, consistency beats perfection. Small efforts made every day leads to big achievements over time. Invest in yourself because highest ROI comes from investing in yourself. Be a lifelong learner by reading books, taking some online courses, learning from mentors, experience new things, be curious, right? Because curiosity is a fuel for innovation and excellence. So before we move on, remember, my friends, whenever you achieve something or whenever you want to achieve something, there is no guarantee you will succeed. But I can give you one guarantee. If you never try, you will never succeed. So don't be afraid to take first step. Keep trying, keep learning, and keep giving your best with complete honesty and dedication. Some things are in our control, like our hard work, our attitude, our commitment. The final outcome is not in our hands. So do your best, keep improving every day, and leave the results to the higher power. Because every successful person was once someone who simply refused to try. So I think enough of motivation talks. Let's jump to the topic. So we have already covered three topics, and so today we'll begin with the next topic, which is review NTN operations. So here we will see key procedures like network access, registration, session setup. So you can say that end-to-end call flow for the NTN. So it is not much different from 5G, but some new things are introduced because in satellite we have specific challenges like delay, Doppler effect, propagation issues, distance. So all these issues we have to adapt and do the minute changes in NTN. And before moving, as I said in many sessions, remember, my friends, NTN is not a replacement for terrestrial networks. It is an extension and a complementary technology that work alongside terrestrial networks to provide seamless connectivity where traditional coverage is limited or unavailable, right? So terrestrial network will always be there. Nobody can remove them. Okay. So let's jump to the topic. So let's see the 5G NTN setup procedures. So in this slide, you see a user equipment, G node B, AMF, all the components of a 5G normal terrestrial networks. So as I said earlier, although the overall procedure looks similar to the standard 5G registration, but several NTN specific enhancements are introduced or upgraded to accommodate larger distance issues like HARQ, Doppler effect, long propagation delay, and satellite mobility. And one more thing, so all these documents are based on various specification of 3GPP, but most of the time I use two specification of 3GP, which is TR 38.811 and TR 38.821. So you can check on 3GP website these two specification, and you can get more details of NTN basics and advanced as well. Okay. So the first step here is the network acquisition. So here the UE is synchronized with the satellite signal. So it receives the master information block and the SIBs. You can see here in NTN a new SIB is introduced, which is SIB 19. This is one of the most important parameter, or you can say thing introduced in NTN. So what are the features or why it is required SIB 19? So you can see that there are various specific information which this SIB provides, right? One is satellite orbital characteristics. So with the help of SIB 19, we can get various parameters like altitude, velocity, inclination, movement patterns of various orbits like LEO, MEO, GEO. So these parameters determine the satellite coverage area, propagation delay, visibility time, and handover in the NTN networks. Then we have this timing compensation. So timing compensation corrects the large propagation delay caused by long distance between user equipment and the satellite. So it ensures uplink transmission arrives at the satellite at the correct time. I will go in detail how it happens, but right now just remember one term called pre-compensation. Right, we'll go in detail with this term, but right now just remember one term. After that, a new word is introduced in NTN. So I have heard this term first time, but if you have heard this term before, that's good. That is satellite affirmers. Okay, what is satellite affirmers? So this is very important information in case of satellite because it contains precise information about the satellite current and the predicted position, velocity, trajectory, etc. UE use this information to correctly accurate various parameters like propagation delay, Doppler shift, and also beam selection. Right. After that, we have beam information. In SIP19, beam information is also transmitted. So it gives various parameter information like beam ID, beam characteristics, so that it enables UE to identify the correct serving beam and helps in seamless mobility. After that, we have various NTN cell parameters also that are transmitted in SIP19. For example, cell ID, frequency, sync information, tracking area, all these information are transmitted in case of SIP19. In short, without SIP19, the UE can't properly compensate for the much longer satellite propagation delay. Okay, so after decoding SIP19, the UE performs RRC setup, which we'll see in the next slide. So then we have this registration request. So once the RRC setup is established, the UE sends the registration request. So unlike terrestrial 5G, the registration request contains NTN specific information. In 5G, we have only one technology or only one NR, so it is NR, right? So here we have various things like RAT, NR over LEO, then RAT can be NR over MEO, and RAT can be NR over GEO. So and AMF also contains the NTN tracking area code list. Okay. So remember, instead of relying solely on the fixed terrestrial cells, the tracking area can be derived from various things like satellite beam, UE location, and moving satellite coverage. So this allows mobility management even though satellite moves continuously, right? Again, what are the steps for registration flow? First, RRC setup is established. Then UE sends registration request to AMF. AMF identify the RAT type. It may be LEO, MEO, or GEO. And AMF updates UE context and maintains NTN tag list. So we have covered RRC setup and we have covered registration request. Next comes the authentication. So it is mutual authentication. So the UE and the core network performs various kinds of authentication like mutual authentication, security key generations, integrity protection, ciphering activation, right? So this step is identical to the terrestrial 5G. And after that, we have this registration accept. So after successful authentication, the OMF, the AMF sends a registration accept message confirming that UE is successfully registered in the 5G core network. So at this stage, the device is attached to the network but can't exchange data at this moment. After that, session establishment is done. So here, the UE now requests a PDU session and it enables IP connectivity, and UE sends a PDU session establishment request to the SMF, right? After that, SM context is created. So SMF create the session management context. So as I said earlier that instead of So in case of 5G, we have only one RAT, which is NR. But in case of satellite, there can be various RAT like NR LEO, NR MEO, NR GEO. So this allows the core network to apply satellite specific policies. After that, we have this SM policy establishment. So the SMF communicate with the PCF. PCF, it's policy control function. So it has various policies such as like QoS, charging, right? So because satellite latency is different from TN, so policy decisions are little bit different in case of NTN. Then we have this satellite QoS parameters. So one important different highlights here is the 5G 5QI configuration. So you can see here number 10, right? So as you know that there can be lots of delay between satellite and the terrestrial network. So delay of 1100 ms is also introduced in case of worst case, right? Because satellite communication introduce various kinds of delay like propagation delay, Doppler shift, processing delay, gateway delay, etc. Right? And this is especially true for geo because it is very far away from Earth. Then we have this PDU session setup complete. Right? Finally, the network completes PDU session setup, and you now has IP connectivity, user plane path, and the access to the data services. Right? So this is the high level call flow of NTN end to end. Right? So what is the key takeaway in the this call flow? The key takeaway is that 5G NTN preserves the same fundamentals of 5G, including like registration, session establishment. Also, it has compatibility with the existing 5G architecture. But it introduce NTN specific enhancements like SIB 19, then tracking area, then latency updated QoS. So to introduce unique challenges of a satellite communication. So these additional upgradation help in seamless integration of various orbits like LEO, GEO, MEO, right? And it provides a reliable connection for remote connections, disaster recovery, maritime, etc. Right? So this is the high-level call flow of NTN networks. So before jumping to next topic, if you have any question, can you write in the chat box? If you have no question, can you write no in the chat box, please? Okay, thank you, thank you. Okay, so let's jump to the next topic. So we have just discussed various differences between TN and NTN. Let's summarize what are the differences according to the call flow. So first is in case of TN, we have standard SIBs, and in case of 5G and TN, we have additional SIB 19 is introduced, right? Why? Because we need various kind of information like satellite affirmers, timing compensation, beam information, cell parameters, all these things, right? So SIB 19 is one of the biggest additions introduced for NTN because user must understand satellite movement and timing before connection. Right? After that, in case of NTN, we have fixed terrestrial cells, but here we have moving satellite beams. In short, instead of users moving between fixed cells, here the satellite beams themselves move over stationary users. So this makes mobility management very dynamic, but also complex as well. So we'll discuss mobility in detail in next few slides. In case of NTN, we have normal tracking area, but here we have NTN derived tracking area codes. So in case of NTN, tracking areas are dynamically derived based on satellite beam location and the user position. So because satellite coverage constantly changes, the network generates the tracking area differently than in TN. So we'll discuss that in detail as well. Then we have standard ad type in case of TN, but in case of NTN, we have NR LEO, NR MEO, and the NR GEO. In case of TN, we have low latency, but here we have high latency is introduced, right? Because in case of TN, latency can be maximum 10 to 30 millisecond. But in case of GEOs, take the example of GEO, latency can be up to 600 millisecond, right? In case of Mio, it can be 200 milliseconds. In case of Leo, it can be 50 milliseconds. So it's very high as compared to TNs. Right? So these are the various differences introduced in case of 5G and TN. So last point is fixed propagation delay and long satellite propagation delay. So these things are, so greater the satellite altitude, the longer the signal travel time. So which directly impacts latency and the network design. Next topic is NTN timing issues and solutions. As we have discussed earlier that there is a large distance between satellites and the terrestrial networks. So various new issues are introduced, but there are also upgradation or you can say solutions available to resolve those issues. So in this slide, we are discussing first the what are the new issues introduced in NTN and also what are the specific solutions for those issues or problem. Okay, so let's jump to the NTN timing issues and solutions. So we know that the biggest challenge in the NTN is the much longer RTT round trip time compared to the terrestrial networks. Since satellites are much farther from Earth than terrestrial base stations, the signal takes significantly longer to travel. So, this will increase the round trip time. So these delays affect several radio procedures. As I said earlier, propagation delay, Doppler shift, all these things, right? And because of that, network adjusts some timers and scheduling mechanism to maintain reliable communication. So let's see the upgradation in case of NTN. So first upgradation is related to RACH. Anybody, can you write the full form of RACH in the chat box? Okay. Thanks everyone for the right answer. So it's random access channel. We know very well the random access procedure is the first step before the communication begins. So in terrestrial networks, timing is relatively predictable, right? But in NTN, we need timing advance pre-compensation, right? Right? In case here we need timing advance pre-compensation, right? We need timing advance pre-compensation. So here the idea is that UE establish the satellite propagation delay before transmitting. It will help signal arrive at G node at the correct time. We have RA response timing window, right? So because the satellite takes longer to return random access response, and the UE waits longer for assuming the attempt has failed. So in TN, the RA response window time is between 10 milliseconds. It is increased to 600 millisecond, 20 to 600 millisecond case of NTN. We have this message 3 timings. So in case of random access, message is transmitted using longer timing window to account for the satellite delay. After that, we have contention resolution. So I have added this slide just to recall these 4 steps which are used in the random access. So first one is the SS1. I know everybody knows these 4 steps, but just to recall. So message 1 is the preamble transmission. So the UE selects a random access preamble from a set of predefined preambles. So these preambles can be roughly 2 categories. One can be short preamble and one can be long preamble format. And the UE also selects a random sequence numbers for the preamble. And after choosing the preamble and the sequence number, the UE transmits the preamble on the PRAT channel, which is physical random access channel. Then we have this message to random access response. So upon receiving the message 1, the G node B sends a response called message 2, and it contains various several important parameters like timing advance, random access preamble ID. We also call it rapid, right? Random access preamble ID. Right? And it also introduced one thing here, which is temporary identifier, which is random access radio network temporary identity. In the message 3, the UE transmits on the push. So message 3 is the push, which may carry certain RRC message like RRC request, right? And in the message 4, we have the contention resolution. So after processing message 3, the G node be sends message 4 to the UE, and message 4, as you know, is the MAC data, right? So the contention resolution message contains the UE identity, confirming that G node B has correctly identified the UE, right? And the contention has been resolved. That's why its message is contention resolution. So I hope you remember these 4 steps: message 1, 2, 3, and 4. After that, we have this uplink scheduling. So in terrestrial networks, uplink grants arrives very quickly. So in 10, but in NTN, the scheduler sends grant much earlier. To achieve this, 3GPP introduced 2 types of offset. One is cell specific K offset, one is UE specific K offset. So in case of cell specific K offset, this parameter is configured to all users in the cell. But UE specific K offset is based on various parameters like satellite distance or maybe beam location, or it is based on propagation delay. So this ensures uplink transmission arrived at the correct time. So let's understand with the simple analogy. Suppose in case of terrestrial network, suppose you have to catch a shuttle and the shuttle is parked outside your house. So you receive a message like come outside now. So you walk out immediately and board the shuttle. That is the case of terrestrial network, right? But in case of NTN, the issue is different. Suppose shuttle is 100 miles away. So the driver calls only when the shuttle reaches your home. You won't have time to get ready. So instead, the driver calls 30 minutes earlier. So you prepare in advance. Same thing in NTN. Case of NTN, UE prepares everything in advance. We'll see in details, but just remember that in case of NTN, UE prepares everything in advance. We have this high ARQ, HARQ. So everyone knows that HARQ is used for error recovery, though through neck and neck feed. Because RTT is much longer in entity, so more HARQ process are required and introduced in case of satellites. The network increases the number of HARQ parameters. But in addition to that, one more thing is introduced, which is HARQ feed. So to improve efficiency, HARQ feedback may be disabled for certain services. Let's understand this with one example. Suppose two cases. One is HARQ enabled and one is HARQ disabled. So let's talk about first case first. So in case of HARQ feedback enabled, suppose a packet is sent from UE to satellite, and the latency here in case of satellite, it can be 600 millisecond. So UE has to wait 600 millisecond before sending the next packet. Same in case of third packet, fourth packet, so on. So since transmitter has to wait for ACNAC after every packet, so it will use or it will result in low throughput, inefficient use of satellite link. Suppose CRQ is disabled. We doesn't have to wait for ACNAC for sending the next packet. So you can send packet 1, packet 2, packet 3, packet 4, and so on without waiting for ACK and NAC. So then the question must arrive that what happened if the packet is lost, right? So if the packet is lost, it can be handled by higher layers like RLC and TCP retransmission later on. So what will be result? Result will be higher throughput and better utilization of satellite resources. Same, we can see the example of video also. So we can send video packet 1, video 2 without waiting for ACK. So it will be introduced in the smooth playback of the video and the better user experience. So in case of satellites, we have continuous transmission, but in case of TN, we have stop and wait transmission, right? So delay impact is very high because of 600 milliseconds RTT, up to 600 milliseconds, right? So in case of HRQ our playback quality is very choppy, but in case of HARQ disabled, it can be smooth. Right. We have this scheduling request. So normally a UE periodically request uplink resources. So in NTN, the scheduling request prohibit timer is extended. So this prevents the UE from sending unnecessary requests. Right. So let's understand this with one example. So in terrestrial networks, how it works. In case of terrestrial networks, suppose UE has to transmit some data. Suppose WhatsApp message, right? So UE sends a SR request to G node, right? And G node B provides the uplink grant as soon as possible, right? And then UE transmits its data because it happens very quickly. So this can be possible in case of TN networks, right? But the challenge is in the NTN because RTT can be up to 600 milliseconds. Suppose case of NTN, UE sends message to satellite or GNOD, right? Suppose it send message. It will take around 270 milliseconds to reach that message, right? After that, G0B grants UL access. So it will take around total 600 milliseconds, right? So if normal timers are used, which is like 40 milliseconds, 50 milliseconds, 120 milliseconds, the UE will assume that its SR scheduling request was lost, right? So network may end up sending duplicates SR. So again, SR will be sent, SR will be sent, right? But because of this, extended timer is introduced, right? So 3GP extends the scheduling request prohibit timers. So since the timer is much longer in NTN, so the UE sends one SR instead of sending duplicate SR. So it patiently waits for the satellite response for so many seconds, and it avoids transmitting the duplicate SRs, and the network process fewer unnecessary requests, right? After that, we have this discontinuous transmission. So we know very well DRX helps save UE battery by allowing the device to sleep between transmissions. But satellite communication has longer delays. Therefore, the network extends both downlink timers and the uplink timers. So this ensures the UE remains awake long enough to receive delayed packets or HARQ transmissions. So this will avoid unnecessary transmissions of the missed message. Let's understood in detail with the help of one example. So in case of TN, right, the UE doesn't keep its receiver on all the times because it would quickly drain off the battery. So what happens in TN DRX cycle? So UE wakes up, it listens for downlink message. If nothing is there, it goes to sleep again and it wakes up again after a short interval, right? This is the process in case of TRX in TN. So significantly reduce the power compensation consumption for the UE, right? But a problem in NTN. What's the problem in NTN? Suppose UE wakes up. And suppose our DNX timer is 20 millisecond, right? So UE listens for 20 milliseconds and nothing is received, right? So in that case, UE goes to sleep. Satellite packet still traveling because of long distance, and packet finally arrives. But when the packet finally arrives, UE is sleeping. So the UE completely misses that packet. So the network may assume that transmission is failed. So send it again, again duplication, right? So how to avoid this problem? So UE sends data and UE stays awake much longer, right? So network response arrived after maybe 550 milliseconds, 600 milliseconds, and so on. So no unnecessary transmissions are required. So this is the process for the DRX. Okay. So if you understand DRX, can you please write yes in the chat box? Okay, thank you, thank you. So these are the issues which are introduced in NTN because of longer distance, and these are the solutions which are provided by 3GPP. And just to mention here, so these are based on 17, but now it's 18 and release 19 is also introduced. So there may be more upgradation as compared to release 17. So here are the most important parameters according to release 17. So you can see that timing advance pre-compensation is not required in NR, but in NTN it is 10 to hundreds of microsecond. In Geo, several milliseconds, right? RA response window, in case of terrestrial network, it can be 2 to 10 milliseconds. So these parameters are very important in case of NTN optimization. So when you do your NTN optimization, so you must know that what can be the minimum value, what can be the maximum value, right? So then we have cell specific K offset. In case of TN, we have 32 slots. So NTN up to 256 slots. And in Geo, there can be many slots, right? HARQ process is also increased from 16 to 32. But in case of Geo, it is disabled. And we have already discussed what are the benefits if HARQ can be disabled, right? And we have discussed about the prohibit timer as well. So in case of TN, it is 128 milliseconds, but in case of Geo, it is increased up to 1 to 2 seconds, right? And before jumping to the next topic, let's recall the Doppler effect, because Doppler effect is one of the most important uh, concept in case of NTN, or you can say in telecom, right? Remember that Doppler effect is not affected by the distance. It's affected only by the speed, or you can say the relative speed. So, what is the Doppler shift formula? You can see that Doppler shift is equal to velocity by c into fc. So, what is v? V is the relative velocity between transmit and receiver. C is the speed of light, and fc is the carrier frequency. Notice that distance doesn't appear in the equation. So Geo is far away from the Earth, but only the relative velocity will affect the Doppler shift, not the distance between Geo and the Earth, right? So here we have two possible situations. So first one is approaching the receiver. So when the receiver is moving towards so when the satellite is moving towards the receiver, the radio waves become compressed. You can see that they are compressed. You can see that compressed. And compression causes seed frequency to increase. Therefore, Doppler shift is positive when satellite is moving towards the receiver. When it is receding from the receiver, now the radio's waves become stretched apart. You can see that they are stretched apart. Right? As a result, the recede frequency decreases and the Doppler shift become negative. So green waveform, satellite approaching. White point, satellite is closest to the receiver. Orange waveform, satellite is moving away from the receiver. Okay. And these are the typical Doppler shifts for different orbits. As you know that for LEO, our altitude is between 500 to 1500 kilometers. For MEO, it should be between 8000 to 20k kilometers, and for GEO, it is around 35k kilometers. But GEO moves at the same speed as Earth moves. So, relative speed of GEO as compared to Earth is zero because it appears stationary for Earth, right? So, in LEO, what can be the Doppler shift at S band? It can be up to 50 kilohertz. For MEO, it can be 30 kilohertz, but in case of GEO, it is around negligible, right? Less than 1 kilohertz. Why? Because in case of Doppler shift, distance doesn't matter, but relative speed matters, right? One of the important bands in NTN is S band. So S band refers to the radio frequency band between 2 gigahertz and the 4 gigahertz, which is widely used for satellite and the mobile communication. So in 3GPP NTN, the satellite band is particularly important because it is allocated for mobile satellite services, MSS, and is used by various operators like Skylo, Ysat, Ligado, Omnispace, AST, etc. So what is the uplink frequency here? It is 1980 to 2010 megahertz. And what is downlink? It is 2170 to 2200 megahertz, right? So what is the Doppler effect? at S band for various orbits. So for LEO, it can be up to 50 kilohertz. For MEO, it can be 20 kilohertz. And for GEO, it is less than 500 hertz, right? So we should remember these values. It will be very helpful in our day-to-day work and maybe in the interviews as well. Okay. And what are the Doppler effects according to various band? For L band, it can goes up to 35 kilohertz for LEO. So this is for LEO. For S band, it can go up to 50 kilohertz. For KU band, it can go up to 350 kilohertz. And for Ka band, it can go up to 600 kilohertz. Okay, next is additional enhancements for NTN. Key improvements to support satellite communication in 5G, 6G. So far we have discussed timings, random access, session establishment. So this slide highlights the additional enhancement introduced by 3GPP to address satellite specific challenges such as high Doppler shift, moving satellite beam, and the mobility management. So first challenge in NTN is Doppler shift. So we have already discussed in details. One of the biggest difference between terrestrial networks and NTN is the Doppler effect. So since satellites, especially LEO satellites, move at very high speed, which is 7.5 kilometers per second. So Doppler shift continuously happen on LEO. Without compensation, there can be various issues related like OFDM subcarriers lose orthogonality. It can increase ICI, right? Inter-carrier interference, decoding performance, degrading, right? So what's the solution? So solution is uplink frequency pre-compensation. So what is this thing? So in this, UE pre-estimates expected Doppler shift using various parameters like GNSS position, like satellite affirmers, SIB19, right? We already discussed, right? With the help of SIB19, satellite affirmers can be shared. So UE pre-adjust the transmit frequency so that signal reaches the satellite at the correct frequency. So instead of network correcting the frequency error, the UE predicts the shift and decompensate the uplink transmission. Then we have this idle mode mobility. So in TN, tracking areas are fixed, cells are fixed. But however, in NTN, the satellite moves and its beam's footprint moves across the Earth. So in traditional TNs, tracking areas were used. The UE would repeatedly perform tracking areas. What's the solution in case of NTN? So NTN solution is fixed geographical area. So what is this thing? So you can say that instead of tying the tracking area to a moving beam, 3GP defined tracking area based on the fixed geographical regions. This means the satellite moves, the beam moves, but the tracking area remains the fixed. Let's understand with one example. Suppose in case of TN, right? In case of TN, we have tower A, suppose tower B, and tower C, right? We have here A1, A2, A3, right? Suppose user sits in the office for 8 hours. Nowadays, nobody sits in the office for 8 hours. At least 10-hour jobs are there. So we have to sit at least 10 hours in the office. Okay. So user sits in office for suppose 8 hours. So cell never change. Tracking area never change because it may be latched to this tower. So no update is required. Right? So everything is stable. But in case of NTN, what happens? In case of NTN, suppose at time 12 a.m. Satellite is here, one beam is here, UE, right? Suppose at 12:10, satellite moved to here, suppose, and beam also moved to here, but UE is at the same location. Okay. So what's the problem? So problem if we use traditional tracking area. Suppose this beam A has tracking area of 101. Suppose beam B has tracking area of 110. Sorry, happened. Just 1 second. Okay. Sorry. Can you please write yes in the chat box if you can see my screen? Okay, thank you. Sorry, I think I have clicked it too hard, my pen, so screen gone. Okay, thank you. Okay, so so suppose this has beam A has TA 101 and beam 2 has TA 102, right? So you can see that UE is still at the same location, but the network thinks that TA is changed. So tracking area update is required. So 10 minutes later, if it is beam C, again tracking area will be required. So there will be TAU, tracking area update, again TAU, again TAU, so tracking update. So this creates unnecessary signaling and it will produce higher battery consumption, AMF overload, and wasted radio resources. So this would happen every time the satellite passes overhead. So what's the solution for this? The solution is the 3GPP has given a wonderful solution, which is the solution given by 3GPP, which is so instead of making the tracking area follow the satellite, right? This is not done in case of NTN. So 3GPP fixed the so 3GPP fixes the tracking area on the Earth surface, right? So think of like drawing a permanent boxes on Earth. Suppose this is the Earth and it has four boxes can be drawn, right? Suppose it is TA 101, this is TA 102, this is TA 103, and this is TA 104. Suppose uh, UE is here, right? Suppose at 1 a.m. this satellite is serving this here, satellite 1 and beam 1, right? And after 10 minutes, satellite 2 is serving this UE, right? So, and beam 2. So you can see that satellites keep on changing, but TA is not changing because TA is now based on the Earth surface, not the movement of satellite, right? So this will save lots of tracking area update. This is a very important concept. So if you understand this concept, can you please write yes in the chat box? Wonderful. Wonderful. Thank you, sir. Thank you. Thank you, everyone. And then we have this idle mode mobility, right? So again, we have this idle mode mobility. Again, in terrestrial networks, tracking areas are fixed, cells are fixed. The NTN satellite moves and the beam footprint moves across the Earth. So if traditional tracking areas were used, the UE would repeatedly perform tracking area updates and it will eventually cause lots of resources wastage. So what's the solution? Solution is fixed geographical area, right? So instead of tying the tracking area to the moving beam, 3GPP defines the tracking area based on the fixed geographical area. So this means the satellite moves, the beam moves, but the tracking area remains fixed on the Earth surface till the time UE is not moving. So this significantly reduces the TA updates. The second remedy is location and time-based measurements. So rather than measuring only signal strength, you also consider the GNSS location and the expected satellite position at a given time. So this allows the network to make more accurate mobility decision. So UE combines the location and the timing information with the radio measurements to predict the correct beam to be used, right? And after that, we have this called connection mobility. So when the U is actively transmitting or receiving data, mobility must be optimized. You know it, right? The first solution here is the event D1. Can you write yes in the chat box if you heard of this term D1 and or no if you have not heard of this term D1? Okay. Okay. Good. Good. Everybody is honest. Some people don't know, and some people know this. Very good. Very good for the honest answers. Okay. So in case of 5G, we have various kinds of handover, right? Like A1, A2, A3, A4, B1, B2, B3, and so on. Basically, if I go with A3, right? If we go with A3, right? So what's the formula for A3? So you can say that measurement or handover will happen if measurement of neighbor is more than measurements of receiver, or you can say that present cell wherever it is latched plus offset, cell index offset plus hysteresis, right? So if this equation is satisfied, only then handover will happen. But in case of NTN, a new term is introduced, which is D1 handover. So in case of NTN, various things are considered before handover. So it can be satellite movement, it can be beam movement, it can be predicted beam. Okay. And other enhancement is CHO. So instead of waiting until the beam edge, the network prepares the target beam in advance. The UE stores the handover command. This is the most important thing. UE stores the handover command. So when predefined conditions are met, and UE executes the handover immediately. So this reduces handover interruption time, rescheduling failure, and these service interruptions. Let's see how it works. As I said, in case of TN, I have given you the formula that Mn should be more than present cell plus offset plus hysteresis, right? Suppose RSRP of Mn of neighbor is more than MP plus hysteresis plus offset, then means neighboring cell is stronger and A3 will be triggered, right? So this is high level. This is possible in case of TN. But what's the problem in NTN? Suppose one UE is stationary. Right? First of all, it is latched to beam one. Right? It is latched to beam one. But after some time, satellite is continuously moving. It is latched to beam two. Right? So the UE may be stationary, but the beam moves on. So the signal strength of beam 1 and beam 2 may be identical, right? So A3 will never trigger, right? So even though the UE is about to leave the beam 1, A3 will never trigger. So what's the solution? So instead of relying only on signal strength, the network uses various things for D1, like its GNSS location, satellite affirmers, which is from SIB19, and the beam reference coordinate. Then it continuously calculates the distance from UE to the serving beam. This is called the threshold 1. Then it calculates the distance from UE to neighbor beam reference, which is threshold 2, right? If threshold 1 and threshold 2 is satisfied, then D1 is triggered. Let's say one example. Suppose beam 1 is at 150 kilometers and our threshold 1 is suppose 140 kilometers, right? So since 150 is more than 140 kilometers, so threshold 1 is satisfied, right? Threshold 1 condition is satisfied. Suppose beam 2 is 120 kilometers and our threshold for threshold 2 is suppose 130 kilometers. So since 120 is less than 130 kilometers, so threshold 2 is also reached, right? So threshold 1 and threshold 2 conditions are satisfied. Then D1 will be triggered, right? I hope you understand this concept. So Manu, have you understood this concept now? Okay, thank you, sir. Okay, so this is how D1 is completely different from A3. So in case of D1, it is dependent on satellite movement, beam movement, and predicted beam exit time. So this allows the network to prepare a handover before UE leaves the satellite beam. Right? And after that, conditional handover is there. So the network prepares the target beam in advance, and the UE stores the handover command. And when the predefined conditions are met, then UE executes the handover immediately. So what are the benefits? So it reduces the handover interruption time, reduces the radio link failures, and reduces the service interruption. So this is particularly very important in LEO because beams moves very faster than the terrestrial networks. So what happens after D1? So UE sends a measurement report to the serving G node B. The report contains serving beam information, UE locations, etc. And the G node B then prepares the beam switching, CHO, conditional handover, and the handover command before the coverage is lost. Right? So again, beam 1, U is currently serving the beam 1. threshold crossed, threshold 2 is also crossed, then D1 is triggered. Target beam is prepared, CH already stored the information, beam changes from beam 1 to beam 2, and instant handover will be happen. So it reduces handover interruption time, reduces radio link failure, and the service interruptions. So what are the difference between event A3 and event D1? So event A3 is signal based, but event D1 is location based. So what's the trigger condition in A3? The neighbor become offset better than the serving. But here, distance to serving beam exceeds the threshold, that is threshold 1, and distance to neighbor becomes beam falls below the threshold 2, right? And it is best for terrestrial cells and NTN. D1 is best for the NTN. So A3 depends on RSRP, but D1 depends on the GNSS position and the beam reference signal. Okay. So again, A3 relies on the signal quality, but D1 relies on the location and the geometry, right? So both events ensure optimal connectivity, right? So that call should not drop before the end. So we can take one real-time example, like imagine you are using Starlink direct to cell while driving in a rural area, and your phone remains in the same location relative to the road. The LEO satellite beams moves overhead, right? Signal strength between the current and the next beam may remain identical. But if the network waited for A3, the handover could be too late. But with the help of D1, the network predicts that you are leaving the current beam based on your location and the beam geometry. So the network prepares the next beam in advance and hands over seamlessly without coverage is lost, right? So we have covered several challenges unique to NTN. Let's quickly revisit those challenges and the enhancement that enables reliable NTN operation. So first challenge is larger Doppler shift and how it can be resolved with the help of uplink frequency pre-compensation. Then we have moving satellite beams, which is which can be resolved by geographical tracking area or fixed geographical tracking areas. Then we have here we have frequent tracking updates in case of NTN, but that can be resolved with the help of location and time-based mobility. So here we have rapid peak transition, but here we have T1. And here we have handover interruption in NTN that can be resolved with the help of conditional handover, right? And rapid beam transition can be resolved with the help of T1. So AI-powered mobility enhancement ensures seamless connectivity for fast-moving NTN environment so that we can have better coverage, seamless mobility, fewer interruptions, and the higher reliability. So we have covered four topics by now. Topic 1, topic 2, 3, and today we have covered fourth topic, which is NTN network operations. Right? I think this is enough for today. So let's recall what we have read today, and then we can wrap up the session for. So first of all, we have discussed what are the advantage and disadvantage of NTN. After that, we have seen various challenges and how to resolve those challenges in case of NTN. Right. After that, we have seen the roadmap as well. So here we have like release 17 is there, then release 18. What are the key enhancement in release 18, and also what are the enhancement in case of release 19, right? So we have RAN 1, which is for radio transmission to physical layer. Then we have RAN 2, 3, 4. So this it is related to protocols, network architecture, and SA. SA means system architecture, and CT means core network, right? So all these what are the enhancement in each release. We have discussed that as well, and we have seen what are the latencies, what are the distance, altitude for different kinds of orbits. All these things we have discussed. In addition to that, we have gone through standards, LEO, MEO, how we can integrate and work them together, right? So, and we have discussed transparent payload, non-transparent payload, regenerative payload. All these things are discussed. In addition to that, we have gone through various bands, and after that, we have also discussed uh, end-to-end call flow for NTN. So we have various steps, right? Basically, 8 steps. First of all, network system acquisition. So SIP 19 is introduced. Then we have random access. Then we have RRC setup, authentication is there, security setup, registration complete, video session establishment, and the user plane data flow is done. So all 8 steps we have discussed in detail. And in addition to that, we have seen that what are the standards which are required, or which are the specification required to make this slide, right? So I have used various specification, but mostly I have used this 38.811, but other specifications are also used for making this slide, right? And we have seen the various key takeaways like SIB19 is introduced, moving beam management, orbit rat identification, specific QoS, handling propagation delays. All these things we have introduced. So we have also seen that in case of terrestrial, RTT is just 8 millisecond, but in case of NTN, it can reach up to 600 milliseconds as well, right? And we have discussed radio procedures, uplink precompensation, D1 parameter, CHO, all these things we have already discussed, right? So what's the summary? So 5G NTN use cases include service continuity, service ubiquity, and service scalability. NTN supports a transparent payload and the regenerative payload architecture. Dual connectivity is supported using the NTN G node B and a terrestrial G node B connection in the to 5GC. The key steps in life of a 5G NTN UE includes system acquisition, registration, and the PDU session establishment. Again, friends, to win in your life, you need 4 things: passion, skill, experience, and target. By watching these sessions and watching these videos, at least your skill can be improved, right? So keep training and keep learning until you get it right. And I request again, please don't forget to subscribe to my YouTube channel. It will be very helpful so that other people can also take advantage of these sessions, right? So I think these kind of sessions are very helpful to improve their knowledge, because I think future is NTN. So we should learn NTN from every resource that is possible. Again, this is me. My name is Gaurav Goyal. And for more details about me, you can check my LinkedIn profile as well. And before we conclude, I would like to leave you with one thought. Knowledge grows when it is shared, and success comes through continuous learning. Again, friends, thank you for your time and attention. Keep challenging yourself, keep upgrading your skills, and never stop learning. Take care of yourself and your family. Until next time, goodbye and happy learning. Thank you.